Today we're picking up with the previous lesson, continuing with testing if events are independent. And this is for not the theoretical probability, but the experimental probabilities, because these are experimental results. If events are independent, it means one event does not affect the probability of the other. For example, let's say we knew that, I'm just making up a number here, 60% of the population has brown eyes. And then we wanted to look at if 60% of males and 60% of females have brown eyes. If that is the case, then gender and eye color are independent because you get the same probability no matter which group you are looking at. So to test if events are independent in a two-way table, we look at, there's a couple different things we could do. We could see if the probability of event A and B out of total is equal to the probability of A and B multiplied together using the product rule, or we can look at just if A and B out of B is equal to A out of the total, something like that. All right, let's take a look to see if the number of siblings and whether or not they walk, bike, or ride a bus or are driven to school are independent. Okay, so specifically, let's look at which ones it wants us to test out. A is the event that a person rides the bus, so I like to highlight what I'm looking at. B is the event of having 3 or more siblings. By the way, it could be that maybe 0 siblings is independent and 1 sibling is dependent. There can be more than 1 in a two-way table. If just because 1 is independent doesn't mean that they all are. So, looking at these events, let's see if they are independent. And this wants us to test out if the probability of A given B is equal to the probability of just A. Okay, so remember, A is riding the bus to school and B is 3 or more siblings. So see if you can find the probability of A given B. That means A out of all the total B's is equal to the probability of A. The probability of A given B would be A out of all the B's. Okay, so A given B would be 9 out of 24. Because that means we're looking, remember, whatever it comes after given, that total goes on the bottom. And the total that have 3 or more siblings is 24, 9 out of 24. And we want to see if that equals the probability overall of riding the bus to school, 75 out of 300 total. So we're looking at these 4 numbers right here to see if they are proportional. And if you do 9 out of 24, that's going to give you 0.375. 75 out of 300 is 0.25. So that means that they are not independent because you get a different probability in the 3 or more siblings than you do in the total that ride the bus to school. So they are not independent because if you ride the bus to school, there's a different percentage that have 3 or more siblings. Okay. Number 7, it says Piper downloads 10 paid apps and 16 free apps on her tablet. 14 of them are game apps, and she paid for 5 of the apps. We want to test if the events paid and game are independent. This does not give us a two-way table. We've got games, we've got paid, we've got free. So I think our 4 things in the two-way table are going to be paid, free, game, and then not game. So I made a little two-way table looking at paid and free apps, game and not game. It says Piper downloads 10 paid apps and 16 free apps. Where would 10 and 16 go in this table? 10 paid would be the total number of paid, and 16 free would be the total number of free apps. It says 14 of them are game apps. So where should I put 14? 14 is the total number of game apps, and she paid for 5 of the game apps. So where would 5 go? 5 would be paid game. Okay? Now let's see if these are independent. We could fill out the rest of the table based on the fact that this adds to 10. 5 plus 9 is 14. 9 plus 7, we have 12. And so the big thing we need to know is the total, which is 26 total apps that she downloaded. And let's see, we're looking at if the events paid and game are independent. If they're independent, that would mean that the probability of whether or not she pays for apps would be the same whether it's a game or not. So we're going to find, looking at the answer choices, the probability of paying for an app overall and the probability of paying for an app out of the games. See if you can figure out if these are independent. The probability that she paid for a game would be, or paid for an app, overall she pays for 10 out of 26 apps overall. And let's figure out if she pays for that same proportion of games, 5 out of 14. Those are not equal. Of course, 10 out of 26 could reduce to 5 over 13. So those are not the same. That means if they're not the same, that means that they're not independent, because whether or not she pays for a app depends on if it's a game or not. It's different if it's a game versus if it's not. Number 8. Which statement is true about whether Z and B are independent events? So I know by my table here, I'm going to be using these 4 numbers when you're trying to find independence from a two-way table. Looking at the answer choices, let's see, all 4 of these want you to find the probability of Z given B, probability of Z given B. And then if I look at these answer choices, this second one says B, then Z, then B. If we want to figure out if they are independent, this first, whatever letter is in the first parentheses needs to be the same that comes first in the second parentheses, because you're looking at the probability of Z given B if it is the same of Z on its own. So that's the one we want to test out. Figuring out if Z given B is the same as B doesn't help us find if they are independent. So we need to find the probability of Z given B and the probability of Z and see if they are the same. If they're the same, then they're going to be independent. See if you can figure that out. The probability of Z given B means out of the total number of B's, whatever comes after the fraction bar, that total goes on the bottom. Out of those, 126 are Z. And overall, the probability of Z would be all of the Z's over the total, which would be 660. Okay, if you divide 126 out of 280, you get 0.424242. You also get 0.424242 if you divide 297 out of 660. That means these are independent events. The probability of Z on its own is the same percentage or probability of Z out of the B category. All right, let's look at another one. It says a shipment of 80 bulbs is made up of 40 red and 40 green bulbs, of which 25% are defective. If 12.5% of the green bulbs are defective, which statement justifies whether or not drawing a red bulb and drawing a defective bulb from the shipment are independent events? This is another one that does not give us a two-way table, so we'll need to make our own. My categories here are going to be red and green, also defective and not defective. It says a shipment of 80 bulbs, so where would 80 go? 80 would be my total number of bulbs. There are 40 red and 40 green. Okay, and it says of which 25% are defective. So we need to figure out how many that is. If 25% of the 80 bulbs are defective, what is that as a number of bulbs? I would need to do 25% of the 80 bulbs to get that 20 of the bulbs are defective. Okay, that means that there'd be 60 that are not defective. Next, it says if 12.5% of the green bulbs, 12.5% would be 0.215 of the green bulbs. So figure out what that would tell us in this table. 12.5% of the 40 total green bulbs, we would need to do 0.125 times the 40 green bulbs. And that would tell me that 5 of the green bulbs are defective. Okay, that would mean that 35 of them are not defective. And if I do 20 minus 5, this gives me 15. I know that 15 plus 25 would add to 40. Now we want to figure out if the number of drawing a red bulb and drawing a defective bulb are independent. Remember, there's different ways to test if they are independent. And if I look at the answer choices, it looks like they are multiplying probabilities together. So out of these, the only one where we're multiplying probabilities together is this one. There are none when we add probabilities together to test if they're independent. We add probabilities together if it's a union or an or statement. So it's not going to be B or D. Okay, see if you could figure out which one of these, if you plug into this formula, would be the case. So we're looking at what we're multiplying together. They're multiplying 1/2 and 1/4. How did they get that? Well, this is the probability of one event overall. Overall, 20 out of 80 of the bulbs are defective. And we would multiply that by the overall probability of red out of the total number of bulbs to see if that equals 15 out of 80 total. And you can see the 15 out of 80 here. 20 over 80 reduces to 1/4. 40 over 80 reduces to 1/2. That does not multiply to give you 15 over 80. So whether or not the bulb is defective depends on if it is a red or a green bulb, because you're not getting the same probability. That means that they are independent events. All right, one of the last things we're going to look at is actually calculating probabilities for independent and dependent events. So remember that when we were testing to see if they were independent, that was for experimental probabilities when they give us data. Now we're going to look at theoretical probabilities when we could just tell whether they're independent or not based on the theoretical probability. So let's talk about, again, the difference between independent and dependent events. Independent events do not affect each other because what you get in the first event does not affect what happens to the probability of the second event. But dependent events, whatever you get the first time affects the second event. Remember, replacement usually means independent. What does that mean? If you draw a card and then you replace it before you draw another card, that's going to change. If you draw a card and keep it, then the probability of drawing that second card would be changed. All right, so let's use the multiplication rule, and we just have to decide if events will be independent or not. So the probability of drawing a king, putting it back, and then drawing a queen. So we're going to find the probability of the first event. The probability of drawing a king would be what? Overall, there's 4 kings out of 52 total cards. Then we're going to multiply that by the probability of drawing a queen. Now, if you put this king back in the deck, then there are still 52 cards to choose from, and how many of them are queens? That would be 4 out of 52 also. Okay, so these are independent events because if you put the card back, then the probability for drawing a queen is the same as if you don't put the card back. You could multiply these and reduce these to get 1 over 169. Now let's look at drawing a king, keeping it, and then drawing a queen. So we're going to find the probability of the probability of drawing a king. 4 out of 52 cards are kings. But if you keep that king, okay, then instead of pulling from 52 cards, if you hold on to that king, how many of them do you have to choose from now? Now there would be 51 cards to choose from if you are holding on to that king. How many of those are a queen? 4 of those are a queen. So this is the probability of a king is 4 out of 52. The probability of a queen, given that you drew a king and are holding on to it, is 4 out of 51. Okay, see if you can multiply and reduce that. So 4 out of 663 if you reduce it. So notice if you hold on to that king and you draw out of 51, that gives you a totally different answer. Now let's look at the probability of drawing a king. So that's still going to be the same. 4 out of 52 of the cards are kings. Let's look at keeping it and then drawing another king. So if you are keeping it, there's no replacement. We need to subtract 1 because next time we would be drawing out of 51 cards. Now let's figure out how many kings there are to choose from because we're drawing another king. How many kings are there to choose from in these 51 cards if you're given event A? So if you're given that you drew a king here, how many kings are there left to choose from if you're holding on to that king? That would be 3 out of 51. Okay, so sometimes you are, if it's dependent, sometimes you're subtracting 1 from the sample space. Sometimes you're subtracting 1 or 2 or whatever from the numerator and denominator. It all depends on the wording. And in this case, since we're holding on to a king, there is one less king to choose from, and there is one less card overall to draw from. If you multiply that and reduce it, you get 1 out of 221. So let's do another one. Lola pulls 2 marbles from a bag containing 4 red, 4 blue, and 12 yellow marbles without replacing them. So remember, without replacement means the sample space is going to change and they are dependent. What's the probability that she pulled out a red marble first and a yellow marble second? All right, so this says and. Remember, if it says and, we're looking at the multiplication rule. So we're going to find the probability of a red marble and multiply that by the probability of a yellow marble, given that she pulled out a red marble first. Okay, what is the probability of drawing a red marble? There are 4 red marbles, and overall there are 1, 2, plus 4 is 6, plus 4 plus 12 gives me that there were 20 total marbles. So first off, you would draw a red. There's 4 out of 20 chances to draw a red. And then we're going to find the probability of drawing a yellow card given that you drew a red marble, not card. So if it's not replaced, okay, is this still going to be over 20? No, now there's only 19 marbles to choose from. And how many of those 19 marbles are yellow? Figure out how many of those are yellow and then see if you can answer the question. Out of those 19 marbles, 12 of them are yellow, okay, because you wouldn't subtract 1 from the 12 because you weren't looking at drawing a yellow first. If you multiply those, that gives you about 0.13. The science club has 5 female and 5 male students. They're going to randomly select 2 people to compete in the upcoming science competition. What is the probability that both chosen are females? So both is kind of another word for and, if you think about it. We're going to find the probability of choosing a female, and we're going to multiply that by the probability of choosing another female, given that the first person chosen was a female, and we're going to multiply those together. So the first probability, choosing a female, would be what? 5 out of the 10 total students are female, okay? Then we want to find the probability of choosing another female, and this doesn't use the words replacement or put back, but once they choose the one female, they're not going to put back in for a second chance because they need 2 people, if that makes sense. So next they are only going to choose from 9 people. And after you've chosen this one female, let's figure out what the numerator would be. How many females out of those 9 would there be to choose from? So if there are, they chose one of these 5, then there would be 4 out of 9. Okay, what do you get for that probability? If you multiply that and reduce it, that will give you C. The Hawaiian language has 12 letters, 5 vowels, and 7 consonants. Each of those 12 letters are written on a slip of paper, put in the bag, and a letter is chosen from the bag, and then replaced. Very important word, replaced there. If the words are, or if the letters are replaced, does that mean it's independent or dependent? If they're replaced, that usually means it's independent because you have you put it back, and the second event does not depend on the first event usually. What's the probability that 2 vowels are chosen? So since they're replaced, we're just going to use the multiplication rule. Find the probability of getting a vowel times the probability of getting another vowel, but the first one would be put back in so it doesn't affect the probability. See if you can figure out what that would be. The probability of getting a vowel is that there are 5 out of 12 total letters. And if you put the one that you chose back in, the second time you're going to have the same chances of getting a vowel, and that's 5 out of 12. So that would be 25 out of 144 total. Next, a 6-sided number cube is rolled twice. What's the probability that the first is an even number and the second is a number greater than 4? Let's figure out if these are independent or dependent. If you roll a dice twice, does the second time, is that affected by what you get the first time? No, so those are independent. So we're going to find the probability that the first roll is an even number and the probability that the second number is greater than 4. We don't have to do given that the first number occurred because it's just the same thing, because if you roll a dice, you have the same chances the second time. Okay, see if you can find a probability if you have 6 sides of rolling an even number and the probability of rolling a number greater than 4, multiply them together. If you roll a dice, there are 6 possible numbers to choose from. And out of those 6, the even numbers would be 2, 4, and 6. So there are 3 of the 6 that are even. The probability of a number greater than 4, if we roll 1, 2, 3, 4, 5, 6, then 5 and 6 would be greater than 4. So that is 2 out of the 6. You still have 6 to choose from the second time you roll a dice. And if you multiply and simplify those, we get 1/6. All right, number 8. A bag contains 11 equally sized marbles. They're numbered. 2 are chosen at random and replaced. Okay, if they are replaced, that's an important point because what does that tell us? That tells us that they're independent. What you get the second time is not affected by what you get the first time because you're putting it back in there. You could draw it again. What's the probability that the first marble chosen is shaded? Okay, and we're going to multiply that by the probability that the second is labeled with an odd number. Since they're independent, we don't have to worry about given that the first one was shaded. See if you could figure that one out. Okay, the probability that these are shaded overall, remember there are 11 marbles, and there are 4 of those that are shaded. To figure out how many odd numbers there are, odd number marbles, the second time you draw, you still have 11 to choose from. And if you count the odd numbers, 6 of them are 11. If we multiply those together, because we're looking at an and situation, we're looking at first is chosen and second is chosen. So we multiply them together. Remember, that's different from the or probabilities when we add them together. Number 9, we're looking at freshmen, sophomores, juniors, and seniors. It says a student is chosen at random to assist with the presentation. The student returns to the group and can be chosen a second time. That's important because we need to figure out if that affects the probability of the second choosing. What's the probability that the first student is a senior and the second is a sophomore? Okay, see if you can figure out whether that's independent or not, and then see if you can find the probability. If that student returns to the group, then they are replaced. So that means these are independent. We need to find the probability of a senior and the probability of a sophomore being chosen. So overall, if we add the total number of people, you would get that there were 80 people. See if you could figure out what this would be. The probability of a senior would be 22 out of the 80. And if that person that is chosen returns, there would still be 80 to choose from the second time. The probability of a sophomore would be 10 out of those. And if you multiply and simplify, that's going to give you a 11 out of 320. Number 10, Nico owns 11 instructional piano books. 2 are beginner, 6 are intermediate, 3 are advanced. 2 books are randomly chosen and replaced after each pick. What's the probability of an advanced? And then, so remember, and is means the multiplication rule, and then a beginner book. So overall, there are 11 books, and since they are replaced, that tells me we're using independence. We're looking at the probability of choosing an advanced book and then choosing the probability of choosing a beginner book. See if you could figure out what that would be. Choosing an advanced book, there are 3 out of the 11 that are advanced. A beginner book, so that advanced book is put back, so we're still choosing from 11. And there are 2 of the beginner books. Multiply those to get 6 out of 121. Number 11, Hero has a stack of cards with numbers from this set written on each card, and he's going to, I guess, draw them out of a hat or something. What's the probability that he pulls out a 3 first and then pulls out a 2 without replacing them? If they're not replaced, that means that they are dependent events. Okay, see if you can find the probability of pulling out a 3. Multiply that by the probability of pulling out a 2 given, so remember we have to say given the first event because they are dependent. There are 8 total numbers written here. The probability of getting a 3, if you choose from those 8 numbers, is 1, 2, 3. There are 3 3s out of the 8. Okay, we're going to hold on to that 3, and then we have 1 less to choose from the next time around. Out of these 7, so if we take one of these 3s away, out of these 7, how many of them are 2s? There are 2 2s out of those 7. You can multiply those to get 6 out of 56, which reduces to 3 out of 28. A hat contains a slip of paper with the name of 26 other students in Eduardo's class, 10 of whom are boys. Eduardo's trying to find his partners for a group project, and he's pulling 2 names out of a hat without replacement. If there is not replacement, remember we're going to be dealing with dependent events. What's the probability that both of the partners will not be boys? So we're going to find the probability of not getting a boy for the first draw. He's not replacing them when he chooses a second event. So that's going to be the probability of not giving a boy, given that the first one was also not a boy. Now, if there are 10 boys, how many would not be boys? That would mean that there are 16 that are not boys. All right, see if you can find the probability of both not being a boy. There are 16 the first time he's choosing. There's 16 students that are not boys out of 26 total students. Okay, the next time he chooses, there are only 25 to choose from. And we started with 16 that are not boys, but we're using one of them here. So now this is going to be only 15 to choose from, only 15 possibilities of not a boy given that time. So if you multiply and simplify those, we get B. A bag contains 1 red pen, 4 black pens, and 3 blue pens. 2 pens are randomly chosen, not replaced. What's the probability that a black pen is chosen first and then another black pen? All right, I know you can figure that one out. If we do 1 plus 4 plus 3, there are overall 8 pens to choose from. And how many of those are black pens? There would be 4 out of the 8 that are black pens. And the next time we're choosing, if they are not replaced, then we're going to only choose from 7 this time. And if it's that first black pen is not replaced, then there would only be 3 black pens to choose from the next time. If you multiply those, that gives you 0.21. Number 14, Nadia's bookshelf contains 10 fiction books, 2 reference, and 5 nonfiction. What's the probability that she picks up a random book, a reference book, does not replace it, and then picks up a nonfiction book? Overall, 10 plus 2 plus 5 means that there's 17 books to choose from. She picks up a reference book. There's 2 out of those 17 that are reference books. If she's holding on to that and it's not being put back, then she only has 16 to choose from. Out of those 16, meaning one of them that was taken away was a reference book, how many are nonfiction? That would be 5 out of the 16. If you multiply and simplify those, we get 5 out of 136. So real quick, let's just recap what all we've done with this probability section. We talked at the beginning about the probability is the chances of something happening. There's experimental and theoretical probability. Remember, experimental is using actual data. Theoretical is just saying theoretically, we don't even need to look at the numbers. We know that there's a 50-50 chance of getting heads or tails or something like that. Experimental is looking at what actually happened. And the more trials there are in an experiment, the closer it gets to the theoretical probability. Sometimes people use simulations to find experimental probabilities. Remember the difference between intersection and unions. An intersection of 2 events means that it needs to be elements that are in both sets, not one or the other. And for intersections, usually the word and means intersection. So how many students are in Math 2 and English 2? And remember, we talked about the probability of finding these intersections. If it's an and, we use the multiplication rule. And then whether or not, or how you use the multiplication rule depends on if it's independent or dependent events. A union of 2 sets usually uses the word or. How many students are in Math 2 or English 2? That means they could be in just Math 2, or they could be in both, or just English 2. And the probability of unions is found by the addition rule. You're adding the probabilities together. And that depends on whether it's mutually exclusive or disjoint. So when we were finding the probability of unions, we asked ourselves if it's disjoint or mutually inclusive. meaning can they happen at the same time? Like, can students be in Math 2 and English 2 at the same time? If they can happen at the same time, you've got to make sure to subtract the overlap so that you're not counting anybody twice. If they're mutually exclusive, you don't have to worry about that. The probability of A and B, if they're mutually exclusive, they can't happen together, then they're going to be disjoint. For example, being a freshman and being a senior are mutually exclusive. The probability of being a freshman and a senior at the same time is 0. So for unions, if something is in A or B, we add the probabilities together. If there's overlap, you have to subtract it. We looked at two-way tables, very important and helpful. To turn into a relative frequency, you divide everything by the total to find all the probabilities. If you're given a two-way relative frequency table with the probabilities, you would multiply by the total to find frequencies. We looked at conditional probability, meaning the probability that one event will occur given that another event has occurred. We use this vertical line to represent given. In a two-way table, the conditional probability is going to be a joint probability or a joint frequency divided by a marginal frequency because it's just out of a certain category. You could do the same thing with the two-way relative frequency. And lastly, we looked at the probability of intersections of two events using an AND. Remember, we have to look at if they're independent or dependent, but for intersections, we use the multiplication rule when it says AND. And if something is replaced before you find the second probability, then they're usually independent. If there is not replacement, meaning if you draw a king and then keep it and then draw another, and then draw a queen, then the second probability is going to be affected by whether or not the first one happened. We look at testing if events are independent by looking at these three tests that you could look at for experimental probabilities. Remember, theoretically, for theoretical probabilities, we can intuitively know if they are dependent or independent. But for experimental, sometimes we test it out. And these are the ways that you could test out if events are independent by looking at if the overall probability of two events happening together is the same as multiplying their individual probabilities together, or if looking at the probability of one event out of the total and seeing if that's equal to that same event out of a certain category.